Today I will discuss on hybridization, a very important topic of chemistry. Hybridization is a mathematical approach to explain the shape of a molecule. If a molecule is planar, hybridization is sp2. If a molecule is tetrahedral, hybridization is sp3. One thing is very important, and we should remember that shape first, then hybridization. We will not say that if a molecule is sp3, it will be tetrahedral, or we will not say that if a molecule is sp2 hybridized, it is planar. In fact, it's wrong concept. We must say if a molecular is planar shape, it is sp2, or if a molecular is tetrahedral, it is sp3. I am giving a bit relation, quite mathematical. Let's see, sigma bond plus lone pair equal to n. Sigma bond plus lone pair equal to 2. The hybridization will be sp. Sigma bond and lone pair equal to 3. Hybridization will be sp2. Sigma bond and lone pair equal to 4. Hybridization will be sp3. And so on. If it is 5, sp3d, 6, sp3d2. One thing is very important, we should remember that in this case, cation or anion will not be considered and pi bond will not be considered. Another important thing, in case of nitrogen, we all should know that there is one lone pair. In case of oxygen, 2 lone pair, and in case of halogen, 3 lone pair. This is also a required concept to use this formula. Let's have practice on basic example 1. In case of methane, here central atom is carbon, and we must remember that hybridization is always performed on central atom, not the total formula. In case of methane, we are getting 4 sigma bond and there is no lone pair, so sigma 4 lone pair 0 equal to 4, it is sp3. Similarly, if I consider ethane, here we get 2 carbon as central atom. Here first carbon sigma bond is 4, second carbon also 4 sigma bond. So in case of first carbon it is sp3, second carbon is also sp3. Ethylene or ethene, we can also perform its hybridization. We all know that in case of ethylene there is a double bond, means 1 sigma and 1 pi bond, and we have said earlier that pi bond will not be considered, so we must consider only sigma bond. Here in this carbon 3 sigma bond, no lone pair, so sp2. Similarly, this carbon, it has 3 sigma bond and pi bond will not be considered, so it's also sp2. C2H2, we all know it is acetylene. So in case of acetylene, we are getting in between 2 carbon 1 sigma and 2 pi bond. With hydrogen, 2 sigma bond. For this carbon, as we know, pi bond will not be calculated or counted, so we are getting only 2 sigma bond and no lone pair. So the hybridization will be sp. Similarly, hybridization will be sp. Let's see, C6H6 is structure of benzene. So if you draw the structure of benzene, we can easily say six carbons all are in sp2 shape. like this, sigma, 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 pi will not be counted, sp2, 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 sp2. So I must say, if you can follow this concept, sigma plus lone pair and the number on saturation with this hybridization, it will be a great help for you to find out the hybridization. So I have said a short technique is a very helpful technique so far, I think, and it will be a great use for you in the exam. For second point, let's see ammonia. As we have said earlier, we must consider one lone pair, though it has not been seen here. So let's have a structural diagram of ammonia. 3 sigma bond, 1 lone pair, so 3 plus 1 equal to 4, so sp3. Let's see water. In case of oxygen, we are getting 2 lone pair, 2 sigma bond, so total number is 4, so it is sp3. Similarly, xenon tetrafluoride, we have to know earlier that it has 2 lone pair. You have to know it. So there is 4 sigma bond, 2 lone pair. So we are getting number 6. I repeat, sigma bond 4 and lone pair 2. So number is 6. Hybridization will be sp3 d2. In case of ammonium, we have said positive or negative or cation anion will not be considered. We are getting 4 sigma bond, so sp3. IF6, if you draw this, you also find the number is 6, so the hybridization is sp3 d2. Let's see example number 3. In this model or structure, we can say sigma is a middle carbon, 2 sigma bond, 2 pi bond, pi will not be counted, so it is sp. Here 2 hydrogen, 2 sigma bond, 1 total sigma 3, so sp2. This one also sp2. It's very important concept. In this structure, a question has been done, that is number of sp2 bond. Let's see first all the hybridization in this structure. Here it is sp2, 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 sp2. It is sp3, sp3, sp2, sp2, sp3, sp3. The question has given that number of sp2 bond. Let's see. Here we are getting a bond sp2 sp2. Here also, and also here. So we can easily say the number of sp2 sp2 bond is 1, 2, 3, 4. So answer is 4. So I think by using this concept sigma plus lone pair, you can solve pretty much solution and you can perform very common hybridizations. There is a special basic. This rule is applicable for the common problems you are given, but in case of aromatic compound where resonance is a factor, here we should remember the very basic. If the component is A double bond B single bond C with a lone pair, this formula should be modified. Like, let's see aniline. We consider A double bond B single bond C with lone pair. Here this pair electron will be considered for resonance. So if I modify the concept sigma plus lone pair, this lone pair will not be considered in this concept. It will go for resonance. So we will count only 3 sigma bond. Here this side will be sp2. Very careful about this, it will not be sp3. Similarly, in case of phenol, one lone pair will be considered for resonance because A double bond, B single bond, C. So if it is considered for resonance, so we can modify the concept sigma, sigma and pi. So 2 sigma, sigma, sigma and 1 lone pair. So 2 sigma bond, 1 lone pair, so it is also sp2. Hope this concept will be a great help for your identification of hybridizations, and in case of your exam, maybe it is your admission test or your day-to-day exam, this concept will be a great help for you. And if you practice some much more examples on this base, I think you got some basic idea on hybridization. So best of luck, wish you a very good life in future. See you again.